Welcome everyone to this new edition of the Asterisk webinars. As you know, Asterisk is a project that works to turn seawater into green hydrogen using clean electrolysis technology. Um, but we're not alone in this great challenge. We collaborate with other projects in what we call the Seawater Super Team. And in this series of webinars, we've started sharing some of the results of our sister projects. Today we've got a representative from the project HySEas. I'll tell you more about that in a second. But just before that, just a quick reminder that this wouldn't be possible without the funding of the European Union and the Clean Hydrogen Partnership, which both back Asterisk and the different projects in the team to develop clean technologies to create better solutions for the transition to the green economy and clean hydrogen. So today here we've got an invited speaker from the project HySEas. He's Nikolaos Margaritis, who's a researcher at the Center for Research and Technology in Greece. Before that, he got awarded a PhD in mechanical engineering at the Aristotle University in Thessaloniki, and now works in the Laboratory of Applied Thermodynamics. His expertise is in the design of experimental facilities and the characterization of clean fuels, including hydrogen, of course, and works a lot in net zero emission buildings, also under the umbrella of the new European Bauhaus. He participates in a lot of European projects, but in this case, he's here to talk about the project HySEas, which, like I said, works alongside Asterisk and another two projects funded by the Clean Hydrogen Partnership to develop new technologies to make clean hydrogen from seawater. So HySEas works in the context of Asterisk at different projects, and they're developing a bipolar membrane water electrolyzer, which is slightly different to the technology we are developing here at Asterisk. So I'm really looking forward to hearing about that. And what they do is they develop a water splitting catalyst, a all-in-one unit specifically designed for seawater, which, as you know, needs special requirements because it's very corrosive of the components. So we need to pay attention to bits and pieces that normally are not the case in hydrogen production. So without further ado, it's just a huge pleasure for me to introduce Nikos Margaritis. I'm really looking forward to your presentation and to the Q&A afterwards, which reminds me, if you have any questions, please use the YouTube chat to send them to us. We've got a couple of people in our team monitoring that. They'll pass them to me, and then we can have a nice Q&A with Nikos at the end of the session. Thank you again, Nikos, for joining us today. Looking forward to your presentation. The floor is yours.
Thank you, Fernando. Hello from my side. Thank you for the invitation to this webinar. I'm pleased to inform you about the HySEas project. Just to share my screen. Okay. Today I will speak about HySEas project, turning seawater into clean hydrogen, and in this project I'm the project coordinator. Before I speak about HySEas, just to mention that I belong to CERTH, Center for Research and Technology Hellas, founded in 2000. It's a legal entity governed by private law under the auspices of General Secretariat for Research and Innovation of the Ministry of Development and Investment. CERTH is a big organization working above 1,500 people. The main funding comes from competitive research projects and small funding from bilateral industrial research contracts, and 10% comes from the government. CERT is autonomous, relying mostly on project and funding from Commission. CERT is split in 5 institutes. We have Institute for Information and Communication Technologies, Sustainable Mobility and Transport Networks, Agricultural Technology and Biosystems Engineering, applied life sciences, but now I'm speaking and I come from the CPERI Institute, the Chemical Process and Energy Resources Institute, and local branch in Ptolemaida, where located our laboratory. So our mission in CERTH is to promote research, development, and innovation. We do high quality scientific research in order to develop innovative products and services with many collaborations with universities, research centers, and industry. Uh, Here you see our vision for the energy transition and environment as a research institute. So we started, as you see here, from fossil fuels, from studying carbon, oil, natural gas, because we are in a region in West Macedonia that has a lot of power stations working burning lignite. So this was substituted from renewable fuels, biomass, waste, renewables. All these keywords are related to projects that we have, biorefineries, new materials, biofuels, alternative fuels, smart buildings, and so on. And so in the last 6 years, we're working also with hydrogen projects as a new fuel coming to replace and to the fossil, let's say, fuels. So in this project, we come and I will show two slides for Hydrogen Hub. It's now a Hydrogen Innovation Hub. It's a big research project that is building now in Ptolemaida, in north part of Greece, with approved budget from about 20 millions in order to construct an innovation hub for the region of West Macedonia that will consist of a photovoltaic park, hydrogen storage systems, electrolysers of 900 kilowatts, battery storage, fuel cells, a test bench in order to measure the characteristics of fuel cells, electrolysers, and components for the hydrogen production. And all this is under construction. It is going to be ready for operation for 3 years until the end of this year. So with this experience in hydrogen and working in hydrogen-related issues, we reached to HySEas Project and the acceptance of funding from European Commission. That we have almost 1 year now working in this project, HySEas, titled Hydrogen from Seawater Electrolysis. Here you can see the call and the topic of the proposal, where the proposal was submitted. The project started 1st of May 2025 and will last 3 years until May 2028. You can see the consortium, where 8 partners from 6 different countries under under the coordination of CERTH. So we have from Norway the Norwegian University of Science and Technology, NTNU. We have SINTEF also from Norway, Manchester Metropolitan University, MMU, from United Kingdom, Revolve as a dissemination communication partner from Spain, HyLab, a green hydrogen collaborative laboratory from Portugal, a Slovenian partner, National Institute of Chemistry, and also another partner from Greece, the National Technical University of Athens and the UAE. And CERTH as the project coordinator. It's a 4 million budget, and the duration, as I said before, will be 36 years. So now we have, let's say, we're in the first, is terminating the first year of the project, and now we are entering into the second year of the project. Here you can see in this image the concept diagram with upstream, midstream, and downstream sections. So what we have here, the midstream, we have the and the upstream we have the seawater as a main input. we have renewable energy in order to power the electrolyzer, and in the midsection, we have the main innovation, that is this bipolar membrane water electrolyzer with cation exchange, anion exchange, a water dissociation cartridge in the middle, taking electricity in order to produce from water, hydrogen, and oxygen. And then in the downstream, we have the production of clean hydrogen, recovery of metals and chemicals for use, and of course using produce hydrogen for transport and energy applications. So the main innovation in this system is the middleware, this new, let's say, type of electrolyzer, in order to be able to produce some hydrogen under difficult situations such as seawater. As you already understand, the problem is that 96.5% of global water is seawater. We have plenty of this water. Green hydrogen is vital for heavy industry decarbonization, but traditional PEM-IM electrolysis relies exclusively on increasing on highly purified fresh water. So in order to avoid this desalination of water, the let's say ultimate solution would be to be able to have a equipment that can handle seawater and produce hydrogen from this. This project gives opportunity to use novel technologies in order to remove organic micropollutants from seawater, capture and recycle precious metals, develop advanced electrolyzer designs, and develop catalysts and membranes based on non-critical raw materials. Benefits is high-efficiency system, sustainable and cost-effective hydrogen production from seawater electrolysis. Of course, there are a lot of challenges, mainly technological, in order to be able to produce hydrogen from seawater. And this case, to the main challenge is that you have to, as input, you have the seawater that is have a complex composition, including sediments, microorganisms, complex ion species, and the conventional PEM electrolyzers are highly impacted from impurities. So there's a lot now for work in the literature in order to improve materials like membranes, catalysts, different transport materials. And the main, let's say, obstacle is that along with the hydrogen production, you have also chlorine production, and chlorine, we don't want it because it's a challenge to the safety, efficiency, and durability of electrolyzers. It's highly corrosive, we want to avoid the superproduction, let's say, of chlorine species. And the expensive precious metals electrolysis cells cannot yet be completely replaced by other similarly efficient materials. So the challenge is to recover these precious metals without significant loss. There's three threats. It's the chloride oxidation reaction. The chloride, we have evolving toxic and highly corrosive chlorine gas. This is the main threat. The catalyst gradual degradation, because the complex ion species, sediments, and marine microorganisms lead to rapid biofouling and material corrosion on standard electrodes. And the third threat is the precious metal dependency. So we want to reduce the heavily reliance on expensive platinum group metals. So the target is to reduce as more as it gets the quantity of these precious metals. HySEas tries to give solutions to this problem and uses an innovative bipolar membrane water electrolyzer, the BPMWE system, in order to improve selectivity for hydrogen and oxygen productions. Non-precious metal catalysts are used for the electrodes, iron, nickel, molybdenum oxides, phosphides, sulfides, carbides. So all these are going to be tested in the period of the project in order to find the best materials for this kind of electrolyzer. and to the electrolyzer to operate in Mediterranean, let's say, seawater conditions without harming marine ecosystems. Sorry, I lost my presentation. Yes. So in this image, you can see this biopolar membrane water electrolyzer device. You can see here the water dissociation catalyst with red, the IL membrane, anion exchange membrane, the uh, the seal excuse me, the cation exchange layer, and the water dissociation catalyst. And this Innova technology developed through HySEas tries to overcome limitations of direct electrolysis of seawater via the simultaneous mediation of ion transport and enforcement of advanced microenvironments. So this device tries to, let's say in simple words, to control the movement of ions in order to suppress the chlorine oxidation and produce some hydrogen from sea water. It also tries to adjust this, but it can handle this by adjusting the pH, let's say, of the system. How do we suppress chlorine oxidation? How do we ensure durability through this, let's say, device? With advanced catalyst engineering, developing highly selective catalysts that strongly favor oxygen over chlorine evolution, engineering low precious metals and precious-free materials with high tolerance to chlorine poisoning, precise anodic pH management to suppress chloride ion transfer to the anode surface, creating selective barriers that block chloride species while maintaining highly efficient ion conduction, and utilizing also from CERTH department Thessaloniki a plasma system. They use a plasma system in order to tune metal oxide nanoparticles, modify surfaces in order to optimize the catalysts that are used in this kind of systems. So the main specific objectives of the proposal, of HySEas proposal, were seven objectives. The first objective is the development of a cost-effective solution for future direct electrolysis of seawater. The second objective was to optimize advanced, cost-effective, and limited CRM electrocatalysts focusing on activity, durability, and selectivity. The third objective is to reduce the experimental efforts, and this is why the specific partners using computer modeling tools in order to simulate all these device and be able to predict, let's say, the behavior of such systems. Of course, this HySEas system is going to be validated at laboratory scale, TRL up to 4, by deploying this device working with seawater as a direct feedstock, including bivalent cations and anions. The fifth objective is to assess the social, environmental, and economic impact of potential industrial application of HySEas system in order to increase the European technology competitiveness in electrolyzer technologies. Prepare the HySEas system for large-scale exploitation. Okay, the target is to after the laboratory to be able to be replicated and to have it exploited exploited by industries, and of course to promote effective dissemination of communication activities in order to consolidate HySEas technology among relevant stakeholders, which is civil society organizations, associations, industrial stakeholders, and so on. As in all proposals, also in these proposals is a specific crucial part is to achieve specific targets that have been written in the proposal, and these targets are explicitly written in the proposal, and the scientific team of HySEas trying to after with experiments and that trying new materials and new, let's say, membranes and catalysts. They're trying all these combinations in order to these main objectives, like current light density, which the target is to have above 0.5 ampere per square centimeter. KPIs related to energy efficiency. The target is to be below the current energy efficiency, below 53, let's say, kilowatt hours electric per kilo hydrogen. A very specific and important indicator is to reduce the quantity of the precious metal. Now it's about 1 to 2 milligrams, but we want to reduce it to 0.2 milligrams in this kind of systems, and of course to have a stable activity with specific hours of in-stack operation. Here, as you can see, again, is the also targets that come from the SREIA KPIs, the clean hydrogen. So there are also some other KPIs for energy consumption in nominal load for the electrolyzers. Okay, degradation, operational flexibility, minimum capacity of the electrolyzer, as I said before, PGM electrode. So all these targets are monitored during the project, and also there is a specific platform in in the clean hydrogen platform. There is a specific platform that yeah, one time per year you go inside and put in and write the inputs from the project related to KPIs in order for them to monitor all the projects that are related to hydrogen and to monitor how they are going, the progress, the safety issues, the legislation, and so on. And some things I want to say about the architecture of HySEas project. There's a lot of work packages in this project. I tried to, let's say, divide it with the peripheral, let's say, work packages you see in dark blue. Project management and coordination, electrolyzer design requirements and restraints in the start of the project. This work package was active, now has finished. We have also work package 13, it's again project management, and 14 work package 14 implementing dissemination activities like work package 7. And the main core of the project are the blue and the green ones. First are the blue ones, OPACAS 3, 4, and 7, where there is the bipolar benchmark and development, novel methods for waste dissociation and electrode catalyst development, single cell preliminary testing and evaluation. Then we these OPACAS are assisted from computational science based simulations. And then we go from the cell, from the cell systems, to one cell systems, we go to stack systems, full experimental campaign in specific stacks, and strategies for recovery, reuse, and regeneration of seawater contaminants. The integrated systems with renewables, and because we want to produce clean hydrogen, so the electrolyzer should be able to get power from all the renewable energy systems. And also there's 11 or package 11 related to LCA analysis, or mostly most of the projects have this whole package in order to perform LCA analysis, life cycle analysis for the final, let's say, output of the project. Here again, you can see the titles of work packages and the lead participant. So we tried each partner to be to lead a specific work package according to specific expertise. And not all the work packages have started until now. As you can see, some work packages start after 19 months. So the first, let's say, 7 work packages have started, and we now just started to have some first results. So the workflow of HySEas projects is including, as you can see, this image, 4 phases. Now we are in the first phase in the material design to select, to research, and to be experimented with different novel materials, layers, porous plastic layers, plasma treated electrocatalysts, precious metal, other precious metals, other metals in order to other compounds in order to replace precious metals. Then we have in parallel with phase one, the phase two, the numerical assessment, which includes multi-scale modeling ranging single cell realization to full stack predictive performance. We have performed some first numerical simulations, and then comes the experimental validation of the unit and stack under relevant realistic conditions. Then in the last phase, the scaling up potential to integrate modeling with renewable energy systems alongside rigorous techno-economic and sustainability assessments. So that now that's that time of the season, we can say that we are here in the first and the second phase. And see, this is a CPOC diagram that you can see here quickly, which are the suppliers, inputs, processed outputs, and customers for these projects. So as suppliers, we have membrane manufacturers, catalyst and electrodes suppliers, producers of porous transport layers. Inputs are membranes, bipolar and ion exchange layers, catalysts, electrodes, gas diffusion layers, seawater samples, synthetic material, experimental and simulation data. The process is to design optimization to this stack bipolar membrane stack architecture to construct and assemble units and stacks to make the conditioning and electrochemical testing of this device across with other validation, iterative cycles, and the outputs of HySEas could be, let's say, the optimized prototypes of these stacks in order to be tolerant to seawater electrolysis. Validated models, performance data, and customers will be the electrolyzer manufacturers mainly, and hydrogen and users such as chemical industry and other ones. As I said before, now it's we have concluded the first year of this interesting project. And the first outputs delivered to the first year was data management plan, was the HySEas master plan from HiLab, the baseline performance and efficiency, the report on baseline performance and efficiency, reporting in the clean hydrogen for the first, let's say, reporting for the first year, dissemination, exploitation, and communication plan, of course, of the project. And we have reached the first 3 milestones of the project. So the vision and the target is to deliver strategic value to Europe in hydrogen issues and related to seawater electrolysis. And this the impact will be in these sectors: environmental resilience, economic and material security, industrial end users. The target is to have zero freshwater footprint for heavy industry hydrogen production, elimination of toxic chlorine byproducts, ensuring safe handling for marine ecosystems, pioneering the recovery and recycling of valuable trace metals and contaminants directly from seawater, reducing the reliance on critical raw materials, providing to electrolyzer manufacturers scalable blueprints for the upscaling of this system, and unlocking localized energy production for coastal chemical industries and offshore renewable energy developers. So each partner has a specific role, and for example, CERTH has the project coordination and a team working in plasma treatment for improved catalysts. MMU, expert in materials characterization, development of more effective membrane and tolerant catalysts. NTNU expert in the electrolyzer characterization, generation of also of metal oxide particles in the cycle of catalyst. The stack performance assessment is going to be performed by HyLab, this collaborative laboratory. The electrolyzer device modeling, including all degradation mechanisms due to chlorine, and microscale modeling will be taken care by SINTEF. DUA, the National Technical University of Athens, will do the life cycle analysis of the product, the output, and Nick do also a performance numerical modeling and DFT calculations. And Evolve has taken the role of dissemination and communication partner for the whole project. So that was, let's say, a HySEas overview of the project, the first, let's say, year of the project, in order to to understand what exactly we are doing in this project. This is the image from the website of the project, and also you can follow us in Instagram and LinkedIn channels. You can see on the screen. And closing, just to inform you that we have the next, let's say, GA meeting in Norway, hosted by NTNU and SINDEF by, let's say, end of May. That's all from my side. Thanks again
Thank you so much,
for the
Nikos, for
invitation.
thank you
I'm
for a very nice presentation.
open to questions from the audience.
Thank you for a very nice presentation. It's great to see how the different projects we had another project a couple of weeks ago. It's nice to see how the different projects are tackling the same challenge, which is creating
Mhm.
green hydrogen from seawater directly. I think you mentioned it at the end of the presentation how it is important to secure the energy strategy of Europe and the energy independence of Europe because we've got so much access to seawater and then we need a technology that could work with that, which sort of brings me to my first question because this was
Mhm.
a main point for the two projects I have presented already, and I was wondering, do you have a particular type of seawater that you using in your study? Are you focusing on the Mediterranean Sea, or are you focusing on specific concentration of salts, or is it just you using like salty water and that's it?
Yes, I think that mainly Mediterranean, but I think they is in the laboratory of MMU. They are going to simulate. They're going to have synthetic, let's say, in the first experiments,
Mhm.
synthetic seawater with changing the percentage of salt and so on. And they have also distilled water, and they're going to play, let's say, with different percentages,
Mhm.
uh, simulating, of course, different marine environments. Okay, the target, of course, is not only Mediterranean, but to be able to resist in different, let's say, saline environments.
So it's different saline environments and then different electrolytes, I'm assuming, to test different compositions and then hopefully
Exactly.
something that resembles the Mediterranean Sea, which
Mhm.
I think it's also a priority in Asterisk because it's the main source of water we've got in Europe on top of the North Sea, the Baltic Sea, and the Irish Sea,
Exactly.
which we're
Exactly.
testing from Galway as well. But yeah, I had a question more of the sort of the structure of the device because already when you mentioned bipolar membrane electrolyzers. I remember like we started Asterisk after another project on seawater electrolysis called Anemel, and I remember a long time ago writing and preparing a whole article about the different types of electrolyzers for water electrolysis. And I don't recall having seen bipolar membrane electrolyzers. So what's the novelty of this type of electrolyzers and what do you think are the advantages versus other alternatives in the market?
Yes, this is a specific type of the membranes, let's say bipolar membranes type of electrolyzer. It's the novelty is that this electrolyzer, if adjusted well, can exploit the advantages from both the PEM and the M electrolyzers. So it tries to, let's say, balance the advantages of these of different electrolyzers, different types, in a bipolar one device by adjusting the pH environment and trying to adjusting the movement of ions in between. So the game changer is how to adjust this kind of system in order to exploit the pros of systems. Of course, we have all the disadvantages and the challenges in this, but I think there is the main, let's say, innovations. The main innovation.
Yeah, I was gonna ask us if you have like double the sort of catalyst because you got the anion exchange and the PEM. I mean, I know it's not the same, but you're combining
Mhm.
two technologies. You're hoping to get
Both.
the best of both worlds, but do you also get the issues of two technologies put together? Like how do you, because you need double the catalyst, the membranes, how do you deal with that? Especially how do you find a combination of catalysts that works in conjunction of the two technologies and without using CRMs? Is that a big challenge for the project?
It's a big challenge, and now we are in this step because they are tried different components. They tried different oxides, carbides, different materials in order to find out which it's most, let's say, ambitious, more relevant for this case. And the last information from MU is that they are have tested, I think, 3, 4 materials, different catalysts, and they have found a, let's say, good combination. But of course, for all in order to have accepted, let's say, results. But this, of course,
Mhm,
needs what treatment of materials you get, what catalysts are the best, let's say, in combination.
mhm.
Uh, this is the target.
I mean, it's definitely a very interesting approach. I like that you know focus on the two technologies and then how to bring them together. That's I mean,
Mhm.
it's a very different challenge to what we have in Asterix. So that's really interesting. I was wondering too, because I saw a couple of mentions to plasma during the presentation.
Mhm.
Could you maybe just quickly clarify what do you use the plasma for? I think it's just for the architecture of the catalyst and the
The
nanomaterials, but
plasma technology, you mean? The
yeah.
CERTH employees okay, uses there's a team in Thessaloniki that has this makes plasma treatment in materials and catalysts that MMU from United Kingdom develop some materials, some membranes,
Hmm.
they are catalysts, and they are sent to laboratory in Thessaloniki, and
Hmm.
they perform this plasma treatment of surface
Hmm.
in order to increase some characteristics of these materials and
Hmm.
to be able to sustain, let's say, the harsh condition of
Of
the
chlorine and
seawater.
seawater.
Yes,
Yeah. So
exactly.
it's more
This is
sort of
the
it's more of a manufacturing technique and sort of nanostructuring of the
yes,
catalyst and the
exactly.
membranes. Okay, that's yeah, because
Yes,
I
they
at some point
play
I saw plasma.
with the porous structure of the
Mm.
material, the surface, and micro some things in order to optimize its characteristics. This is
Yeah,
the
because I saw plasma at some point and I thought, oh, energy consumption is going to be high, but if it's just the manufacturing and the nanostructuring, we're all going to have the problem in terms of manufacturing catalyst that's going to be costly, regardless of what technology you use. And I guess that's
yes.
also something you take into account in the LCA studies. As
Mhm.
you know, it's going to need a little bit more energy to manufacture the catalyst, but if at the end you get more efficiency, that's definitely a good trade-off. Like you can
Exactly.
make a nicer, more efficient catalyst with the plasma technology. That's really cool,
Mhm.
and I think that's also very novel and interesting in the sense of using new technologies in nanotechnology, that's really cool.
Mhm.
So yeah, I'm just checking quickly if we have anything from the audience, but I'm actually not seeing anything at the moment. The good thing about this is that the webinars like stay hosted on YouTube, so hopefully we may get more engagement later on. So I think because of the duration and because we don't have any more questions, I think it's probably the perfect moment to bring this to a close. I just wanted to very quickly thank you again, Nikos, for collaborating in this webinar and joining us today. I don't know if you've got anything else to add from your side before I close.
Uh, just also again to thank you for this invitation, and if you want to follow the project and to, I think that we will have more, let's say, concrete results, and that in the second year of the project and the third year of the project. So this is the time that we get into the deep, let's say, core of the project. This is the time of decision.
Yeah, it's the same for us. I mean,
Yes,
it's almost like the first year is all about, meeting the consortium, meeting
exactly.
everybody, laying out the priorities, and having the first work packages finished. And now we're down to business. We need to create the technology and spend the last, 18 months in our case, um, growing in TRL and creating a technology that's actually
Yes, this is
interesting for commercialization.
optimum target. Yes.
Yeah.
Yeah,
So
that's good.
yeah, with that, I think I'm gonna just quickly close the webinar, not without thanking again our funders, the European Commission and the Clean Hydrogen Partnership for allowing us to bring these projects, not only Asterisk but also HySEas and the rest of the sister projects to life. If anybody's interested in staying in touch, we've got our webpage, our social media channels, which I think are somewhere above here, like YouTubers do. So you can sort of go on LinkedIn and Blue Sky and follow us, follow our webpage, and then also please do follow the recommendations by Nikos and follow HySEas as well. We're working separately, but at the same time working together towards a solution for clean seawater electrolysis and green hydrogen. With this, again, Nikos, thank you so much for joining us. We'll have a webinar in the next few weeks with the last one of our sister projects, and we are really looking forward to that. Stay tuned to our newsletter and webpage for the details. And yeah, thanks again, everyone, for joining. See you very soon.